Imagine this. One day, you wake up to find that Earth is no longer the modest blue marble we've always known. Instead, it has ballooned into a monstrous gas giant, rivaling Jupiter itself. Gravity has shifted. The skies are swirling. Your steps feel like carrying a mountain. Welcome to a reimagined Earth, the size of Jupiter. This isn't just science fiction. This is a mind-bending what-if scenario rooted in real astrophysics. And today, on Infinity Beyond, we'll walk you through what would happen if Earth grew to become the king of planets. Jupiter's radius is 11 times greater than Earth's, and its mass, a staggering 318 times more. So if we suddenly scaled Earth up to that size, while keeping the same density, our planet would weigh 4 times more than Jupiter. That's not just big, that's monstrous. And this size wouldn't just look impressive from space. The very fabric of life would change, beginning with gravity. Gravity on this supersized Earth would increase by roughly 11 times. That means everything you do, walking, lifting, even blinking, would take immense effort. Just getting out of bed might require the strength of a professional weightlifter. Want to go grocery shopping? Better train like a power lifter first. Scientists believe humans can survive under stronger gravity, but only up to about 5 times what we experience now. 11 times? That's well past our biological limit. To survive, we'd need help. Robotic exoskeletons, engineered muscles, or perhaps entirely new human physiology. Our cities would crumble under the strain. Buildings would collapse unless reinforced with futuristic materials. Roads would crack. Skyscrapers? They'd never stand a chance. Transportation as we know it would be impossible. Air travel? Grounded. Cars? Too heavy. We'd need anti-gravity tech or underground tube systems to survive the crushing environment. This new Earth would be less a planet and more a pressure cooker. But there's more. Jupiter's massive gravity traps layers upon layers of dense gases: hydrogen, helium, ammonia. If Earth were that size, it would start pulling in an atmosphere similar to gas giants. The sky would become an endless swirl of clouds, storms, and alien mists. Thunderstorms would rage for weeks. Hurricanes could span continents. A single lightning bolt might be 100 times more powerful than what we know. And beneath that sky, humanity would learn to live in bunkers or die in the open. Now let's talk about the human body. Your heart would struggle to pump blood. Bones would be under constant stress. Breathing would be harder. Over time, evolution might push us toward being shorter, denser, and stronger. Or maybe we'd abandon our bodies altogether. Upload consciousness into machines. Adapt to survive, or vanish. Increased gravity would also wreak havoc on oceans. Tides would surge like tsunamis. If Earth gained moons to balance the gravitational madness, their orbits might become chaotic, causing destructive tidal waves regularly. Entire coastlines could vanish. The oceans might become so deep and compressed, they'd form new, unknown underwater ecosystems. Or, in a wild twist, Earth's own pressure might turn it into a mini Neptune, an ocean world with storms circling its equator endlessly. So what if Earth became the size of Jupiter? It wouldn't just be a bigger version of our home. It would be a new world, one that challenges everything we know about biology, physics, and human resilience. Cities would fall, species would die, but perhaps, in the chaos, new life would rise. Maybe not human, but something adapted. This isn't just a thought experiment, it's a testament to how finely tuned our world is. A reminder, Earth's size isn't just a number, it's a miracle. Imagine this. You step outside your reinforced home, and within 3 steps, your legs tremble. Not because you're weak, but because every movement feels like you're carrying a car on your back. Your joints scream. Your muscles burn. It feels like you've run a marathon, except you've only walked 5 meters. And you can forget about jumping. On this super Earth, even raising your arms above your head is exhausting. Chairs aren't just for comfort anymore. They're survival gear. Every bench, railing, or wall becomes a lifeline to rest your aching body. To survive here, we'd need to rethink human biology. Hearts must be stronger, capable of pumping blood uphill against enormous gravitational resistance. Lungs must be more efficient, muscles denser, and bones thicker than ever before. Even your skin might need to adapt to higher pressure. Over generations, evolution could reshape us. Future humans might be short, squat, and muscular, built like powerlifters or compact tanks. And if natural adaptation isn't fast enough, enter genetic engineering. We'd design stronger humans, tougher organs, and maybe even gravity-resistant artificial limbs. In this world, technology is survival. Everyone wears powered exosuits just to function, the kind you'd expect from a sci-fi movie. These robotic skeletons wrap around your body, amplifying your strength, protecting your joints, and keeping you mobile. They'd be as common as smartphones are today. Custom-fitted, solar-charged, and AI-assisted. Kids would grow up learning how to calibrate their suits instead of riding bicycles. Hospitals, full of neural stimulators and pressure-adaptive machines. Gyms, replaced by biolabs offering muscle enhancements. Life would become a constant balancing act between biology and machine, but even eating becomes a challenge. With gravity pressing down on your chest and gut, digestion slows. Stomach muscles strain to churn food. Swallowing thick substances, risky. Meals are re-engineered to be light, nutrient-dense, and easy to digest. Liquid diets might dominate. Think protein gels, enriched broths, and gravity-adapted nutrition packs. Even drinking water could be tricky. Liquid doesn't flow the same way under high gravity. We'd need pressurized drink systems, bottles with internal pumps to push water to your mouth. Children born on this super Earth would need to be stronger from birth. Their bones would be reinforced through supplements. Crawling and walking would take longer, but once adapted, they'd grow into a new kind of human, one built for pressure. Aging, however, becomes dangerous. As joints weaken and muscles deteriorate, high gravity takes a heavier toll. Medical care becomes more complex, with robotic supports and regular physical therapy, essential just to stay alive. Lifespans may shorten, or science may push harder into anti-aging tech, creating implants, synthetic organs, or even partial body replacement. Now, what about how we live and move? Buildings can no longer reach for the skies. Architecture shifts inward. Subterranean homes and domes, built to withstand pressure from every direction. Materials like carbon nanofiber, synthetic graphene, and ceramic alloys become standard. Transportation systems would evolve too. Cars resemble slow-moving armored tanks, low to the ground with ultra-strong magnetic suspensions. High-speed trains, now running through pressurized tunnels. Space elevators and skyports, grounded indefinitely, unless we unlock anti-gravity propulsion. Life under this pressure isn't just physical, it's psychological. People would be more cautious, deliberate, and perhaps slower-paced. Quick gestures and spontaneous movement? Dangerous. Culture could evolve to reflect this, emphasizing mindfulness, stability, and inner strength over speed and agility. Social roles might shift. Jobs requiring physical labor would be heavily automated or robotic. Artists, thinkers, and engineers could become the new pillars of society. It's a world of adaptation, but also one of ingenuity and resilience. Outro. Soft music returns. Voice lowers for dramatic finish. So, could humanity survive on a Jupiter-sized Earth? Yes, but only with radical innovation, biological transformation, and technological unity. We would become something new, a fusion of flesh and machine, a species shaped by gravity and driven by will. This isn't just science fiction. It's a mirror to how adaptable we really are, and a glimpse into the power of science to transform what seems impossible into survival. Jupiter has 95 confirmed moons. Earth, just one. Now imagine our Earth-sized Jupiter orbited by not one, not two, but dozens of moons, some as large as Mars, others barely larger than asteroids. At night, the sky would be alive, a majestic cosmic ballet of glowing spheres gliding across the heavens, some bright as mini suns, others casting long shadows across cities. But beauty isn't the only thing they'd bring. Each moon has gravity, and when multiple moons tug at Earth's oceans, gravity turns into chaos. Tides wouldn't just rise and fall, they'd twist, slam, and surge unpredictably. Imagine 3 or 4 supermoons pulling in different directions. Coastal cities could face flooding several times a day. Entire regions might become uninhabitable. Super high tides, whirlpool effects, strange wave patterns. The oceans themselves would become a chaotic dance floor for water. And if 2 moons aligned, a megatide would occur, possibly engulfing entire coastlines. Culturally, multiple moons would reshape our perception of time and meaning. Ancient civilizations based their calendars and festivals on a single lunar cycle. With 20 or more moons rising and setting in intricate patterns, every night would become a cosmic show, unpredictable, beautiful, and perhaps terrifying. Religions might form around the largest moons. Poets would write sonnets to the dancing satellites. Astrologers would invent complex systems with dozens of moon signs and planetary alignments. The night sky wouldn't just be admired, it would be interpreted and worshipped. But there's a dark side to this lunar abundance. Moons exert torque on a planet. With many satellites, Earth's rotation could wobble, a phenomenon known as axial precession. This wobble would mess with seasons, length of days, and long-term climate stability. In some regions, winter might last for years. Elsewhere, monsoons could vanish or last decades. A stable climate, as we know it, could break down entirely, throwing ecosystems into disarray. More moons equal more eclipses. Lunar eclipses, solar eclipses, double eclipses, triple eclipses. There might be days where the sun is blotted out multiple times, sending ripples of shadow and cold across the planet. While beautiful to witness, such frequent eclipses could have strange effects on plant life, animal migrations, and even mental health. Farmers might struggle to plan crops. Migratory animals could get lost. Circadian rhythms shattered. Even human behavior might shift in response to constant changes in light. With so many moons orbiting in tight proximity, the risk of collisions increases. Moons could crash into each other over millions of years, creating dazzling rings like Saturn's. Or worse, debris could fall to Earth, raining meteors and causing localized extinction events. Our sky would not only be beautiful, but dangerous. We'd need advanced space monitoring systems, orbital defense platforms, and predictive AI just to keep track of what's coming and when. Now, for the upside. Some moons, like Ganymede or Europa, are large enough to have atmospheres, underground oceans, or even magnetic fields. If our new moons shared similar traits, humanity might find colonization opportunities. We could build space elevators, launch platforms, or entire moon cities, hopping between satellites like cosmic islands. Imagine cities glowing across the moon's surface, Earth visible like a giant blue and red swirl in their skies. From a single habitable world, we could become a civilization of moons. Jupiter doesn't just dominate the solar system with size. It also radiates death. Its enormous magnetic field traps charged particles from the solar wind, creating a radiation belt thousands of times more intense than Earth's Van Allen belts. If you were floating near Jupiter, unprotected, you'd receive a lethal dose of radiation in under a day. Now, imagine Earth developing that same monstrous field. Magnetic fields are partly determined by a planet's size, rotation speed, and core composition. A Jupiter-sized Earth, with a faster spin and molten iron core, would likely generate a magnetosphere far larger than our current one, stretching for millions of kilometers into space. But this wouldn't be a shield, it would be a trap. Solar particles would get caught, spiral, accelerate, and bombard the upper atmosphere. Instead of protection, we'd be surrounded by a giant radioactive halo. Satellites would fry. Even our most hardened space tech wouldn't survive long in that environment. GPS systems, weather satellites, communications networks, all rendered useless within days or weeks. Space agencies would need to build radiation-hardened spacecraft, protected with lead, magnetic shielding, or even active deflection fields. Human missions to orbit? Almost impossible, unless new radiation-blocking tech is invented. We'd become prisoners on our own world. The increased radiation wouldn't stay in orbit. As charged particles slam into our atmosphere, they would create hyperauroras, dazzling lights stretching far beyond the poles, visible even from the equator. But they come at a price. These particles would strip away the ozone layer, increasing ultraviolet radiation at the surface. Cancers, mutations, and ecological collapse could follow. Clouds might glow at night. Lightning storms might become electrified with gamma bursts. And rain? Potentially laced with radioactive isotopes. Life would need to evolve or perish. Surface species would struggle. Plants exposed to UV spikes might wither. Animals could suffer mass extinctions. Human skin cancers would skyrocket. But underground life, or deep ocean species, they might thrive. Humanity might retreat into bunkers, domed cities, or subterranean arcologies. Civilization would go underground, literally. We might even bioengineer humans resistant to radiation, with reflective skin, rapid DNA repair, or even synthetic blood. To survive in this radiation hellscape, we'd need a new kind of infrastructure. Shielded orbital rings to reflect or absorb particles. High-altitude energy filters using electromagnetism. Global early warning systems for solar storms. Entire industries would rise, focused not on exploration, but on defense from our own planet's field. And perhaps we'd start building space stations farther from Earth's deadly grasp. This version of Earth is still beautiful, majestic even, but dangerous beyond anything we know. And it might change how we view the universe. No longer the gentle blue marble in space, Earth becomes a reminder that scale is power, but also peril. That what protects can also destroy. And that survival isn't just about technology. It's about adapting to truths beyond our control. Saturn's rings aren't solid. They're made of countless particles of ice, rock, and dust, some smaller than grains of sand, others the size of houses, all orbiting in harmony. Now imagine a scaled-down version of that surrounding Earth. A shimmering band of light stretching across the sky, not painted, but real, physical, ever-changing. Reflecting sunlight by day, glowing silver under the moonlight. For Earth to gain rings, something dramatic must happen. Possibility 1. A moon shatters. Torn apart by Earth's gravity, its remains forming an orbiting disk. Possibility 2. A massive asteroid impact, launching billions of tons of debris into orbit. Possibility 3. Artificial creation. Humanity building a ring of satellites, mirrors, or debris for some megastructure purpose. However it happens, the result is breathtaking. Earth's own ring system, spinning like a celestial crown. Depending on where you live, the view changes dramatically. In places near the equator, the rings would arch across the sky, like a cosmic highway overhead, visible even in daylight. In northern or southern latitudes, the rings might appear more vertical or vanish entirely, seen edge-on as a thin line. But from space, the planet would look like a sci-fi painting. Blue oceans, white clouds, green continents, all encircled by shining rings. Astronauts would call it the most beautiful world in the cosmos. Rings would rewrite human history. Ancient civilizations would build temples aligned with ring shadows. Myths and legends would form around their movement. The sky would no longer just mark time, it would tell stories. Religions might worship the rings as divine symbols. Flags and empires might rise under the crescent arcs they cast. Even art, architecture, and storytelling would shift, inspired by the ever-present glowing arcs overhead. Rings wouldn't just change the sky, they'd change our soul. Surprisingly, yes, rings would block sunlight in specific regions, casting long shadows at certain times of year. That could cool parts of the planet, disrupt ecosystems, delay crops, or create permanent twilight zones depending on the ring's orientation and thickness. They might also reflect extra sunlight, brightening Earth's nights unnaturally. No more stargazing from certain cities. The rings would outshine the Milky Way. In short, the rings would be beautiful, but powerful. But rings aren't just pretty. They're made of space debris, and that debris travels at thousands of kilometers per hour. One wrong nudge, from a satellite, an asteroid, or even gravitational drift, and ring material could descend into Earth's atmosphere, causing firestorms or orbital collisions. Low Earth orbit would become clogged and hazardous. Space missions would be harder. The ISS? Probably retired or moved farther away. And over time, without replenishment, Earth's rings could decay, raining down in fiery showers that light up the sky. Yes, and maybe we will. Future civilizations might design synthetic rings using solar panels, reflective films, or smart satellites, creating a planetary art installation visible across the solar system. These rings could power Earth with solar energy, regulate temperature, serve as orbital highways, or even defense systems. A cosmic mix of science and art and engineering, a new kind of planetary signature. We might not wait for a moon to break, we might build the rings ourselves. Outro, soft, ethereal music. Narrator's voice slows. So what if Earth had rings like Saturn? We'd live under a sky of silver, a world more beautiful than we've ever known, but one shaped by shadows, light, and the constant hum of cosmic motion. It would be a different Earth, a more poetic one, but also a world where the sky reminds us, every single night, that we are part of something vast, fragile, and ever-orbiting. Scene 1. Jupiter's Moon Empire. Jupiter has 95 confirmed moons. 4 of them, the Galilean moons, are so massive they'd be planets if they orbited the Sun. These moons, Io, Europa, Ganymede, and Callisto, are more than celestial rocks. They have oceans, volcanoes, magnetic fields, and possibly life. Now imagine a Jupiter-sized Earth with similar gravitational pull. It wouldn't just attract space debris. It could capture moons or form them during planetary evolution. Earth, reborn as a gas giant, could become a lord of moons. Scene 2. How moons are born. There are 3 main ways moons form. Co-formation, forming alongside the planet in its birth disk. Capture, pulling in nearby asteroids or dwarf planets. Collision, like our moon, born from a giant impact. A super-Earth with strong gravity would likely form dozens of moons during its chaotic youth, or steal them later through gravitational encounters. Asteroids, rogue bodies, even other planets' moons could be lured into its orbit. Over billions of years, Earth's sky would fill with a diverse cast of satellites. Scene 3. Life on the moons of Earth. Some of these moons might be rocky, others icy. But if Earth is massive and warm, it could create powerful tidal heating, like what happens on Jupiter's moon Io. That means volcanic moons with lava oceans and unstable crusts, or subsurface oceans like Europa, hidden beneath frozen shells, warmed from below. These moons might evolve life of their own, independent ecosystems, alien biospheres, strange evolution shaped by extreme environments. And one day, we might live on them. Scene 4. The rise of a lunar civilization. If Earth has a dozen or more moons, some of them would be colonizable. They'd be easier to reach than Mars. Smaller gravity wells, more frequent launch windows, and constant visibility from Earth. Imagine floating cities above frozen lakes, under-ice colonies glowing in Europa-like oceans, mining operations on metallic moons, entire civilizations rotating around a blue giant in the sky. Earth wouldn't be just a home planet, it would be the capital of an orbital empire. Scene 5. Orbital mechanics and moon madness. But there's a problem. Too many moons, and things get complicated. Moons tug on each other, orbits shift, collisions happen. Over time, some might crash into Earth, fall into the atmosphere, or get ejected into space. To survive long-term, these moons would need careful orbital spacing, or maybe human intervention using orbital engineering. With advanced tech, we could stabilize moon orbits, terraform surfaces, create artificial satellites to balance gravity. We'd become architects of a lunar system. Scene 6. A sky filled with stories. From Earth's surface, the night sky would be alive. Dozens of moons, each with its own orbit, color, brightness. Some rising together, some eclipsing others. A constant, moving canvas. Calendars would be lunar-based. Cultures would associate different moons with different emotions, deities, or omens. And explorers would look up, not toward distant stars, but toward worlds just overhead. Moons you could see and touch. The human dream of living among the stars? It would start right above us. Scene 7. Earth, the center of a lunar nation. This version of Earth isn't lonely. It's a hub, a beacon, a parent to a family of moons, each unique, each alive in its own way. We'd build spaceports to connect them, trade routes, defense systems, research outposts studying alien geology, chemistry, and perhaps alien biology. Earth would no longer be just a planet. It would be a system, and humanity would become multi-world. Outro. Emotional, awe-filled music fades in. So what if Earth had its own moon system? It would change everything. Our skies, our science, our future. And as we stand beneath the glow of a giant blue world, encircled by rings and followed by moons, we'd remember we were once a single planet, but we dreamed bigger. Scene 1. What is a brown dwarf, really? A brown dwarf is not a planet, and it's not quite a star either. It's what scientists call a failed star. Too massive to be a planet, but not massive enough to ignite into nuclear fusion like a true star. Brown dwarfs emit a faint heat, a dim glow. They sit silently in the dark, barely visible in space, slowly cooling over billions of years. And unlike planets, they're born from gravitational collapse. Now ask yourself, what if Earth somehow underwent that collapse? Scene 2. Earth's impossible mass gain. To become a brown dwarf, Earth would need at least 13 times the mass of Jupiter, over 4,000 Earths packed into one. It's impossible under natural conditions, but in a speculative universe, maybe through runaway accretion, alien megastructure experiments, or collision with a gas giant, Earth reaches the threshold. The pressure builds. Gravity intensifies. The core fuses deuterium for a brief moment. And then, Earth is no longer a planet. It becomes a brown dwarf. Scene 3. The transformation begins. The transformation wouldn't be quiet. As Earth collapses, the crust implodes. Oceans vaporize. The atmosphere is stripped. Temperatures spike to thousands of degrees. Gravity becomes overwhelming. Tectonic plates grind into dust. Within days, Earth becomes a superheated, glowing sphere. Its radius shrinking, but its mass growing. The light it emits is dim, infrared, but deadly up close. Our home becomes uninhabitable. A fireball drifting in silence. Scene 4. No longer part of the solar system. The mass of a brown dwarf would be enough to disrupt the solar system. Orbits of the Moon, Mars, even Jupiter would shift slightly. If Earth retained its orbit, it would no longer be Earth, just a burnt-out husk glowing dimly. But more likely, its increased mass would pull it inward, or even slingshot it out of the solar system entirely. Our once lush world cast adrift between stars, alone, invisible to the naked eye. Scene 5. What happens to humanity? In this scenario, Earth as we know it ends, but perhaps humanity survives, escaping in time, building cities on Mars, Titan, or deep space stations. We might look back at the dying light of Earth, a ghost planet, and remember it not as a loss, but as a warning. A reminder that mass, energy, and gravity are delicate balances, that no world is permanent, and that even planets can die. Scene 6. Could brown dwarfs host life? But here's the twist. Brown dwarfs may not be entirely dead. Some have moons, large enough to retain heat, oceans, and even atmospheres warmed by internal activity. If Earth became a brown dwarf, could its moons become refuges of life? Perhaps Europa-like moons orbiting this dark sun could sustain microbial life, or advanced civilizations living in artificial habitats, basking in the residual warmth. The irony? Life may end on Earth, but begin anew around it. Scene 7. The philosophy of planetary death. This segment isn't just science fiction. It's cosmic reflection. Everything in the universe transforms. Stars are born, planets collide, systems fall apart, and sometimes even a world like Earth might evolve into something unrecognizable. The death of Earth wouldn't be the end of the story. It would be the beginning of a new cosmic identity. Earth, not as a planet, but as a celestial mystery. A fading ember in the dark. Outro. Slow, melancholic piano with space visuals fading to black. So, what if Earth collapsed into a brown dwarf? It would mean extinction, transformation, and perhaps strange new life. A future where Earth doesn't shine in blue and green, but glows dim in deep infrared. A future where our planet is no longer a home, but a memory. Scene 1. How stars are born. Stars are born in stellar nurseries. Vast clouds of gas collapsing under gravity until fusion begins at their core. To ignite fusion, a body needs immense mass and pressure. The smallest known stars, called red dwarfs, require at least 75 times the mass of Jupiter. That's over 24,000 Earths. So for Earth to become a star, it must gather a monstrous amount of gas. Maybe a supernova shockwave triggers a runaway accretion. Or a cosmic accident, like being swallowed by a molecular cloud, fuels Earth's transformation. One day, it reaches the threshold and ignites. Scene 2. The moment of ignition. The core of this mega-Earth compresses. Hydrogen atoms fuse into helium. Nuclear energy bursts outward. Radiation pressure stabilizes the collapse. A new star is born, not in a distant nebula, but right here, where Earth once orbited peacefully. The Earth you knew, forests, oceans, cities, vaporizes in seconds. In its place, a small but radiant red dwarf star, burning at thousands of degrees, Kelvin, glowing a soft crimson. It will shine quietly for trillions of years. Scene 3. The solar system realigns. The birth of a second sun in our solar system shatters everything. The moon is obliterated by the heat. Mercury and Venus are incinerated or flung into new orbits. Mars is scorched. Jupiter's delicate balance is disrupted. Saturn's rings scatter. Uranus and Neptune drift. The once harmonious dance of planets becomes a gravitational battlefield. The solar system becomes binary, two stars pulling everything in a dangerous tug-of-war. Scene 4. A new Earth, elsewhere? With Earth now a star, humanity cannot survive on its surface, because there is no surface anymore. But what if we'd escaped in time? Perhaps by then we had already colonized Titan, Europa, or even a nearby exoplanet. We look back at the glowing red dot in the sky and say, that was Earth. Our new star could even become a light source for nearby moons, warming them just enough to awaken oceans, perhaps even life. Earth no longer nurtures life on itself, but around it. Scene 5. The science and scale of our star Earth. Our new red dwarf star would be smaller than the Sun cooler, 3,000 or 4,000 K, redder in hue, and longer lived than any star in the sky. While the Sun will die in 5 billion years, a red dwarf can burn for trillions. Earth, most now a star, would outlive every planet, every civilization, every memory. It would become a quiet sentinel in the galaxy, long after we are gone. Scene 6. Cultural and philosophical reflections. From ancient myths to modern science, Earth has always been a symbol of life, the birthplace of humanity. But what if that symbol changed? What if Earth became a symbol of transcendence, no longer a cradle, but a source of light? Religions would evolve. Stories would be rewritten. Star maps would mark Sol A and Terra B, a dual system with two suns, one golden, one red. And in those stories, Earth wouldn't be the home we left. It would be the flame that lit the way forward. Scene 7. Earth as a galactic beacon. A billion years from now, alien astronomers might scan the sky and detect a faint red glow. They'd catalog it, study its spectrum, perhaps even send probes. But they'd never guess that this modest red dwarf, dim and unassuming, once held oceans, poetry, civilizations, and dreams. That it once had life. We would be a legend wrapped in hydrogen. Outro. Emotional music builds to a swell. Visuals of Earth fading into a red glow among stars. So what if Earth became a star? It would mean the end of our world and the birth of something eternal. A transformation beyond biology, beyond borders, beyond time. A world that once gave life, becoming light itself. Scene 1. What is a black hole, really? A black hole is the ultimate endpoint of mass and gravity. It's not just a dense object, it's a point of no return, where space-time bends so severely that nothing, not even light, can escape. At its heart, the singularity, where the laws of physics collapse. Black holes typically form from the deaths of massive stars, but what if somehow Earth became one? Scene 2. What would it take for Earth to become a black hole? Earth doesn't have enough mass to collapse naturally, but if compressed by some external force, an alien device, quantum accident, or artificial gravity weapon, Earth could be forced past the Schwarzschild radius. That's just 9 millimeters for Earth's mass, the size of a marble. In an instant, our entire planet would collapse into a point, invisible, yet infinitely dense. The process would be violent, catastrophic, and final. Scene 3. The moment of collapse. As the collapse begins, crust fractures, core implodes, and gravitational waves ripple outward. Light bends, time slows, and in one final flash, Earth disappears. What's left is a black sphere floating silently where Earth once was. Perfectly black, perfectly cold, perfectly deadly. No explosion, no remnants. Just a warped hole in the fabric of space. Earth is now a black hole. Scene 4. What happens to the Moon and nearby planets? The Moon, without Earth's solid form, now orbits a tiny yet massive singularity. If no mass is lost, it might continue circling, oblivious to the planet's death. But radiation surges, magnetospheres collapse, and gravitational pull shifts. Over time, lunar orbit destabilizes. The Moon could spiral in and vanish. Mars, Venus, even satellites might be drawn closer, especially if Earth's mass grows by absorbing space debris. Earth's black hole becomes a cosmic vacuum, slowly feeding on its surroundings. Scene 5. What happens to time near Earth's black hole? Time near a black hole doesn't behave normally. From afar, the black hole appears frozen in time. But for anything close, time slows dramatically. An astronaut falling in would experience minutes, while the universe outside moves forward by thousands of years. Earth's transformation would create a time distortion, a bubble where past, present, and future blur. Near the event horizon, cause and effect stretch like rubber bands. Physics breaks down. Space becomes twisted beyond comprehension. Scene 6. Could we detect it from space? From a distance, Earth's black hole would be invisible, except through gravitational lensing. Light from background stars would bend around it, creating a shimmering ring, the photon sphere. Astronomers might see distant stars flicker. Spacecraft might vanish. Orbits shift mysteriously, the signature of a silent killer. Earth, once alive with color, now hides in darkness, known only by its hunger. Scene 7. Could anything escape? Could we survive? If humanity had escaped in time, maybe we live among the stars now, looking back. Perhaps we built a station orbiting the black hole, using it as a power source, like a sci-fi Dyson sphere harvesting Hawking radiation. Maybe we study it, mourn it, name it. Terra Nova Collapse, Sector 3, Origin, Earth. Or maybe, we never escaped, and the black hole is all that's left. Silent testimony to what once was. Scene 8. Philosophical reflections. The end of Earth's identity. A black hole. Earth is the final erasure of identity. No cities, no oceans, no fossils, no memory. Just a gravitational ghost. It's the ultimate irony. The more Earth compresses, the more it disappears. And yet, the more power it holds. Earth doesn't explode. It transcends into pure force, into mystery. Outro. Quiet piano and soft spey ambience, screen fades to black. So, what if Earth became a black hole? It would mean the erasure of everything we know, but also the creation of something ancient, powerful, and eternal. A reminder that even worlds can fall, and yet leave behind echoes in the dark. Scene 1. How could Earth be moved? Moving an entire planet would take unimaginable energy. But it's not impossible in theory. A gravitational slingshot gone wrong. A near collision with a rogue planet. An alien civilization repositioning Earth for a megastructure. Or humanity's own desperate attempt to escape a dying sun. Whatever the cause, Earth is ripped from its orbit and sent drifting millions of kilometers outward. The further it goes, the darker it gets. Scene 2. The immediate aftermath of the shift. As Earth leaves its stable orbit, everything begins to unravel. Seasons stop, days stretch or vanish. The Moon's orbit wobbles. Temperatures plummet. Within weeks, equatorial zones dip below freezing. Within months, the oceans begin to solidify from the top down. Photosynthesis halts. The food chain collapses. Humanity is forced underground, or into domed cities powered by nuclear cores and geothermal energy. The surface becomes a howling wasteland of ice. Scene 3. The death of sunlight. At Earth's current orbit, 150 million kilometers, sunlight takes 8 minutes to arrive. At the edge of the solar system, over 6 billion kilometers away, sunlight is 1,600 times dimmer. The sun becomes just another star in the sky. No warmth, no daylight, just endless blue-black twilight and starlight flickering through blizzards. Photosynthetic life disappears. Natural cycles die, and with them, entire ecosystems. Scene 4. What happens to the atmosphere? As temperatures drop below the 100 degrees Celsius and keep falling, Earth's atmosphere begins to condense and fall as snow. First, carbon dioxide, then nitrogen. Eventually, even oxygen freezes. The sky clears, not because of peace, but because there's no air left. Breathable zones are reduced to pressurized underground bunkers, domes, or maybe fusion-heated arcs powered by AI and machine farms. Above ground, Earth is silent, still, airless. Scene 5. Could anything survive? Strangely, yes. Life underground might endure, powered by geothermal vents or fusion. Deep ocean trenches, if not entirely frozen, could host microbial colonies. And if humanity was prepared, we might build mega-habitats with simulated ecosystems and artificial suns. Earth would no longer be a planet for life. It would be a spacecraft, drifting in silence, home to survivors, dreamers, and digital minds preserving memory. Scene 6. Earth's new neighbors. Out here, Earth is among strange company. Sedna, a mysterious dwarf planet with a 10,000-year orbit. The Oort cloud, a shell of icy bodies surrounding the solar system. Comet worlds, frozen visitors from the deep dark. Occasionally, Earth might pass near them, exchange icy matter, pick up new moons, or collide with wandering debris. The solar system no longer holds Earth in balance. Earth is now an interstellar drifter. Scene 7. Could Earth ever return? Maybe. With advanced propulsion, planet-sized thrusters, or gravitational redirection, Earth might spiral back toward warmth, or orbit a new star entirely. Or if all else fails, journey into interstellar space. A dead world, a frozen arc, a time capsule of everything we were. Scene 8. Humanity's legacy in the ice. Frozen monuments remain. Satellites entombed in frost. Cities sealed under glaciers. Flags still standing where the wind no longer blows. Future explorers, alien or human, might one day discover this world. Find frozen books, data cores, recordings. Discover oceans locked in crystal. Seeds waiting in vaults. And perhaps light a fire again, not just for survival, but for memory. Outro. Slow piano under whispering winds. Camera pans across the frozen Earth, glowing faintly in starlight. So what if Earth was moved to the edge of the solar system? It would become a silent relic, a drifting echo, a place where life once danced and may one day return. Scene 1. Could Earth orbit a black hole and survive? Surprisingly, yes. If a black hole has the same mass as our Sun, and Earth orbits it at the same distance, 150 million kilometers, the gravitational pull would be the same. Earth wouldn't spiral in. It would remain in stable orbit. But there would be one critical difference. No light, no warmth, no fusion. Just darkness. Scene 2. Total eclipse. The death of daylight. A black hole doesn't emit light. There's no sunrise, no daylight. The sky becomes a permanent night. Stars might bend and distort behind the black hole's event horizon, forming a glowing halo of lensed light, like a celestial crown. But for Earth, the temperature would drop fast. Without an artificial sun, the planet freezes. Just like in segment 10, but even faster. Earth becomes a shadow world. Scene 3. Could we simulate the sun? If humanity foresaw this change, we might prepare. Build orbiting fusion reactors, artificial suns, to warm the surface. Use Dyson swarms to collect background starlight and redirect it. Or construct a planetary shield to trap geothermal energy. It wouldn't be Earth as we know it, but it could be habitable for those who adapt. Scene 4. The view from Earth. Gravity's distortion show. Looking up from Earth's surface, the black hole would appear both terrifying and hypnotic. A perfect sphere of blackness, surrounded by the photon ring, a glowing circle of distorted starlight. Gravitational lensing, light from stars bent around the void. Occasional stellar flares, if the black hole is feeding. The sky would shimmer and swirl in strange patterns. You wouldn't just see the cosmos, you'd see time, twisted. Scene 5. What happens to time near a black hole? Here's where it gets mind-bending. Einstein's theory of relativity tells us, the closer you are to a black hole, the slower time flows. If Earth orbits close enough, time for us could pass slower than for the rest of the galaxy. 1 year on Earth, 100 years for someone farther out. This is called gravitational time dilation. And it's not fiction. It's been measured. Living near a black hole means living in the future, relative to everything else. Scene 6. Could Earth get closer? The habitable zone of a black hole. In 2019, researchers proposed that spinning black holes might emit enough accretion light to warm nearby objects. If Earth orbits just outside the event horizon of a feeding black hole, near what scientists call the Goldilocks zone of a black hole, radiation and light from the accretion disk could mimic sunlight. In this razor-thin orbit, Earth could technically sustain life. But one miscalculation, and Earth falls inward. Game over. Scene 7. Risks, tidal forces, and deadly jets. If Earth ventures too close to a massive or spinning black hole, it would face extreme tidal forces, known as spaghettification. The planet could be stretched, warped, or shredded. Some black holes also emit relativistic jets, beams of radiation that could sterilize entire worlds. Living in this system would mean constant monitoring, constant escape plans, constant fear, a place where gravity is king, and one error is extinction. Scene 8. A civilization beyond time. But if humanity survives, thrives, adapts, we might become something new. A civilization living in deep time, aging slowly, evolving technologically faster than the universe. Our knowledge would leap ahead. While centuries pass for us, millennia pass elsewhere. We could become guardians of knowledge, watching stars let one die while we remain unchanged. Earth, once home to primitive humans, becomes a timeless observatory. Outro. Soft, cosmic music. Earth shone glowing faintly near the dark orb of the black hole. So what if Earth orbited a black hole? It could work, if we're careful, if we adapt, if we redefine what it means to be alive. It would be a colder world, a darker world, but perhaps a smarter one. Scene 1. The setup. Mass versus volume. Let's define the rules. Earth keeps its mass, 5.97 by 1024 kilograms. But its diameter shrinks from 12,742 kilometers to 1 centimeter. A planet compressed into the size of a marble, denser than any known object short of a singularity. This isn't just theoretical, it's a recipe for disaster. Scene 2. Gravity intensifies beyond belief. Gravity depends on mass and distance. Shrink the radius, and gravity at the surface skyrockets. Standing on this marble Earth, you'd be crushed instantly. Pulled inward with the force of 1029 times Earth's gravity. Even light can't escape this pull anymore. That's right. Earth would instantly become a black hole. Scene 3. Wait, isn't this just another black hole? Yes. In fact, this is how black holes are formed. If you compress Earth below its Schwarzschild radius, about 9 mm, it becomes a singularity. So this isn't just a dense planet, it's the death of planetary physics. Space curves, time warps, everything nearby gets sucked in. Earth, as a marble, becomes a gravitational monster. Scene 4. What happens to the Moon and orbiting satellites? The Moon would continue to orbit the marble Earth for a while, as long as the mass stays the same. But any satellite passing too close would be torn apart by gravitational tidal forces. Eventually, the Moon might drift closer and cross the event horizon, vanishing forever. The same goes for anything else: debris, asteroids, even spacecraft that wander too near. Earth becomes a trap in space. Scene 5. Visual distortions and time dilation. To a distant observer, Earth's marble-sized black hole would be nearly invisible, except for the light-warping lens it creates. Starlight behind it bends, creating rings of distorted space. But near it, time slows. Seconds stretch. Gravity redshifts light into deep infrared. If you hovered just outside the event horizon, you'd see the future unfold, while barely aging yourself. Earth, once a home, is now a clockwork prison of time. Scene 6. Could anything survive nearby? Survival would be unlikely. Temperatures around the black hole might be near absolute zero, unless there's accretion matter heating the surroundings. But even then, radiation bursts from infalling material could fry anything unshielded. Maybe spacefarers, alien or human, might place stations in stable orbits, using the black hole for science, energy, or propulsion. Or perhaps AI minds float nearby, studying this strange relic of a once-living world. Scene 7. Why this matters in real physics. This thought experiment isn't just fantasy. It teaches us about the limits of matter, how space, time, gravity, and mass interact at cosmic extremes. It echoes real dangers, like black hole formation, neutron stars, and the collapse of superdense materials. And it reminds us, scale matters. Not just what a planet is made of, but how much space it takes up. Scene 8. From marble to mystery. Imagine an alien species discovering a black hole the size of a marble. They scan it, study its mass, decode its structure, and discover it once was a planet, with oceans, civilizations, music, art, a place where children once played, trees once swayed, and clouds once danced in the sky, all now compressed into a perfect sphere of silence. Earth, not forgotten, but transformed. Outro, somber piano melody. Camera pulls back from the black sphere floating among stars. So what if Earth was shrunk to the size of a marble? It would vanish, not in light, but in gravity, leaving behind a mystery, a distortion, a wound in space where a world once was. Scene 1. From planet to moon, the capture. Let's imagine a powerful gravitational event, perhaps a near collision or intentional redirection, that sends Earth on a new trajectory. As Earth nears Jupiter, the gas giant's gravity grabs hold. Earth is pulled into orbit, joining Jupiter's massive moon system, becoming a new Galilean moon. Only now, Earth is no longer sovereign. It orbits a world 317 times its mass. The blue planet becomes a follower. Scene 2. Earth's new view of the sky. From Earth's surface, the sky changes forever. Jupiter looms overhead, dozens of times larger than the moon, filling the sky with storms, bands, and swirling colors. It dominates day and night. Its gravity tugs at our oceans. Its radiation belt pulses in the distance. The sun is still there, but smaller now, dimmer, a background actor to Jupiter's spectacle. Night becomes surreal. Scene 3. Tidal forces and orbit drama. Jupiter's gravity isn't gentle. It pulls. It squeezes. It stretches. Earth's tides grow monstrous. Coastlines are reshaped daily. Earth's orbit might become eccentric, triggering intense seismic activity as internal pressures build. Volcanoes erupt more frequently. Earthquakes become common. The planet trembles under the influence of its new master. Jupiter doesn't just own Earth's orbit, it begins to reshape its core. Scene 4. Radiation hazard from the Jovian belt. Jupiter has the strongest radiation belt in the solar system, stronger than the Sun's solar wind at close range. If Earth orbits within this zone, the radiation exposure would be lethal to unprotected life. Earth's magnetic field might help shield us for a while. But without precautions, the atmosphere could erode, electronics could fry, satellites would fall, civilizations would have to build radiation-proof cities or escape underground. Scene 5. Earth joins a crowded sky. As a moon of Jupiter, Earth is no longer alone. Now it shares space with Io, Europa, Ganymede, Callisto, each a world in its own right. Earth becomes part of a dynamic system. Io, volcanic and unstable. Europa, with hidden oceans. Ganymede, with its own magnetic field. Callisto, ancient and cratered. It's not just a solar system. It's a moon civilization. A family of worlds, exchanging materials, gravity, and light. Scene 6. What happens to life on Earth? If Earth orbits far enough from Jupiter's radiation, life might survive, even thrive. The gravitational energy from Jupiter could warm Earth's core. In the absence of strong sunlight, Earth might develop bioluminescent ecosystems, powered by geothermal and tidal heat. Plants might evolve to harvest Jupiter-reflected light. Animals might see in infrared. Life adapts, as it always does. Earth, once a sovereign planet, becomes a self-sustaining moon. Scene 7. Cultural shifts and human identity. With Earth no longer a planet, human psychology changes. We're no longer inhabitants of Earth the planet, but citizens of Jupiter's system. Calendars change, based on Jupiter's orbit, not Earth's solar year. Stories shift. New myths emerge. Jupiter as the celestial king, Earth as its favored child. Our origin remains Earth, but our identity becomes Jovian. Scene 8. The philosophical twist. Earth humbled. For billions of years, Earth stood tall, and a blue jewel, home to life, dreams, and civilizations. Now it's a moon, smaller in role, dependent on another. But maybe that's not weakness. Maybe Earth learns humility, to share its light, to orbit something greater, to become part of a system, not the center of one. Sometimes we grow not by rising, but by joining. Outro. Cinematic strings swell. Earth and Jupiter rise together over a horizon of stars. So what if Earth became a moon orbiting Jupiter? We'd lose our throne, but gain a new perspective, a new sky, a new family of worlds, a new chapter in the cosmic story. Earth, not just a planet, but a world reborn. Scene 1. What are planetary rings made of? Rings are usually made of ice crystals, dust, rocky debris, broken moons or comets. These materials orbit at incredible speeds, forming razor-thin disks around gas giants. But on Earth, with an atmosphere, those same rings would behave very differently, because they'd collide with air. Scene 2. Can rings exist inside the atmosphere? No, not for long. Earth's atmosphere creates drag. If ring particles pass through the atmosphere, they slow down rapidly and fall to Earth. So for rings to slice through our sky and survive, they'd need constant replenishment, artificial stabilization, or to exist in low orbital altitudes with minimum air resistance. In this scenario, we imagine mega rings orbiting at 200,300 km altitude near the upper atmosphere, with parts dipping into the mesosphere. It's impossible naturally, but terrifyingly fun to explore. Scene 3. A sky like you've never seen before. Look up and forget the blue sky. Instead, see towering arcs of light and shadow stretching from horizon to horizon. Sometimes bright as the moon, sometimes glowing with auroras caused by atmospheric friction. At night, they'd glow like neon scars, slicing through constellations, lighting up cities. In daylight, they might cast moving shadows across the land. Your noon sun might suddenly dim, not from clouds, but from a band of orbiting debris drifting above your head. Scene 4. Atmospheric friction. Beauty versus destruction. But with rings inside the atmosphere, friction becomes fire. Debris constantly burns in the upper sky, creating continuous meteor showers, high-altitude sonic booms. Occasional debris falls that devastate the surface. Skies would hiss and glow. Airplanes would have to reroute. Satellites would be shredded. Storms could become electrically supercharged from ring dust ionization. Rain might fall through plasma trails. The sky becomes not a shelter, but a dynamic battlefield of energy. Scene 5. The climate impact of rings in the sky. Rings that pass through or hover near the upper atmosphere would block sunlight like a massive filter. This could cool certain regions by day, create cold shadows under ring arcs, disrupt global wind and temperature patterns, cause mini ice ages. If thick enough, Earth would have striped climates, some places in permanent dusk, others in reflective glare. Agriculture would need to adapt to a dancing shadow system above. Scene 6. Living under danger. Cities, culture, survival. Societies would evolve with ring safety protocols. Cities might build shield domes to deflect falling debris. Skyscrapers would be designed with anti-impact plating. Spaceports would shut down during ring flare cycles. Schools might teach children what to do if the sky starts burning. And culturally, we'd worship the rings, fear them, integrate them into art, flags, language, belief. Our myths would speak of the sky's edge and gods who walk its lines. Scene 7. Could humans build such rings on purpose? Maybe. Mega engineering projects of the future could create low-orbit energy rings used for solar collection, microwave transmission, orbital defense shields, or even space elevators with debris capture functions. These artificial rings might be controlled, stabilized, and maintained, giving Earth a luminous crown that doubles as infrastructure. But one failure, and the sky would fall. Scene 8. A planet of perilous beauty. An Earth with atmospheric rings would be a wonder to behold, but also a place of constant risk. A reminder that sometimes beauty cuts deep, and that the sky, once soft and open, could become the sharpest thing we know. Outro. Emotional string music as camera pulls back from Earth, surrounded by luminous, glowing rings flickering through clouds. So what if Earth had rings that cut through its atmosphere? It would be spectacular, terrifying, mythical. A world where light burns, where shadow dances, and where the heavens never sleep. Scene 1. Is this even possible? The concept of co-orbital planets. Yes, in theory. In orbital mechanics, there's a phenomenon called trojans or co-orbitals, objects that share an orbit with a planet, located at stable points, Lagrange points, or in symmetrical positions across the Sun. Jupiter has dozens of these. Even Earth has tiny co-orbital asteroids. But what if another full-sized planet, let's call it counter-Earth, existed in the same orbit as us, just hidden behind the Sun? We'd never see it, but it would always be there, like a gravitational mirror. Scene 2. How would it remain hidden? The perfect balance. Imagine, Earth orbits the Sun in 365 days. So does counter-Earth, exactly opposite us, always 180 degrees away, on the far side. From our perspective, it's always behind the Sun, cloaked in blinding light. We'd never see it with the naked eye. Even our telescopes might miss it, unless aligned precisely or equipped with solar-occluding lenses. For millennia, it could stay secret, unless something disturbs the balance. Scene 3. What if it's discovered? The moment of shock. Let's say our probes, telescopes, or solar missions detect anomalous gravity. Then, a shadow. Then, images. A second Earth. Same mass, similar atmosphere, orbiting our same path. Panic ensues. Wonder erupts. Religions are rewritten. Conspiracy theories explode. Have they always been there? Are they watching us? Or are we the duplicate? Humanity enters a new age of cosmic reflection. Scene 4. The risk of collision. Orbital instability. In reality, orbital symmetry isn't eternal. Gravitational nudges from Jupiter, Saturn, or even passing comets could destabilize counter-Earth's perfect opposite position. If it drifts off course, even slightly, the two Earths would begin a slow spiral toward confrontation. In a few centuries, or millennia, they might approach a near miss, a cataclysmic collision, or a moment of first contact. Two worlds, one path. The stakes, everything. Scene 5. What would life be like on the twin Earth? Assuming the twin Earth evolved under similar solar conditions, it could be a mirror of our own, with oceans, continents, clouds. But life might be completely alien behind us in evolution, or far ahead. What if they developed faster, built megastructures, watched us from afar, or feared us? A first contact with our cosmic reflection would be the most profound moment in human history. Scene 6. Could the two Earths communicate? If detected, we'd send probes, signals, lasers. But remember, any signal takes time to curve around the Sun, and the Sun itself blocks direct view. To talk to our twin, we'd need lunar relays, solar sailing satellites, or a spacecraft slingshotting around the Sun. It would be a challenge, but the reward? Knowledge, unity, or rivalry. Scene 7. Philosophical implications. The cosmic doppelganger. The existence of another Earth raises deep questions. Are we unique? Is life inevitable? What if they ask the same questions? The idea of a co-orbital twin forces us to confront our identity, not as rulers of Earth, but as cohabitants of a shared path. We're not alone. We're not even central. We're one side of a cosmic coin. Scene 8. The final risk. Orbital convergence. Eventually, gravity wins. The orbits decay. One planet is pulled ahead, the other drags behind. Their paths tighten. In the final act, the two Earths appear in the sky, visible to one another. Mass panic, global awe, diplomacy, or destruction. In a scenario called a horseshoe orbit, the planets dance past one another in a rare celestial ballet. Or, in the worst case, impact, a collision of worlds that ends both. Outro. Swelling music. Visuals of two Earths nearing each other with glowing atmosphere trails behind them. So what if Earth shared its orbit with another planet? It would be thrilling, dangerous, awe-inspiring. A reminder that the universe doesn't just allow for mirrors, it sometimes builds them. Let's do the math. Current Earth mass, 1 Earth. New Earth mass, 10 Earth's radius, stays the same. What does that mean? Surface gravity increases from 1g to almost 3g. Escape velocity jumps from 11.2 km to over 22 km. The atmosphere thickens, the stakes rise. Earth becomes a super-Earth without changing its shape. Scene 2. Walking becomes a workout. With 3x gravity, a 60-kilon human now feels like 180 kilograms. Walking becomes laborious. Running? Nearly impossible. Joints deteriorate faster. Bones fracture easily. Humans would need to evolve stockier, more muscular bodies, or wear powered exosuits just to move. Children might struggle to grow. Elders might not survive the strain. Earth becomes a world of strength. Scene 3. Our cities collapse. Most of today's buildings, bridges, and skyscrapers are designed for 1G. Under 3G, structures sag under their own weight. Roads crack, elevators fail. Aircraft can't generate enough lift. Civilizations would rebuild everything with new materials, stronger foundations, and underground construction. Even trees would evolve thicker trunks or never grow tall again. Scene 4. The air becomes heavy. Gravity pulls not just on your body, but on the atmosphere. With stronger pull, the atmosphere becomes denser and thicker. Pressure at sea level increases dramatically. Oxygen is compressed, easier to breathe, but toxic at high levels. Sound travels faster, but with distortion. Skies darken, sunsets redden, and storms intensify. A denser atmosphere also traps heat, potentially creating a runaway greenhouse effect. Earth becomes hot, heavy, and humid. Scene 5. Water, oceans, and megawaves. Oceans would become deeper, heavier, and more compact. Tides become smaller, but waves hit harder. Underwater pressure increases. Deep sea life becomes even more alien. Rivers erode land faster. Evaporation slows, affecting rainfall. Coastal ecosystems collapse. Inland areas become more stable, but less biodiverse. Water still flows, but it feels heavier. Scene 6. A new biosphere emerges. Life adapts. Insects shrink or disappear. They rely on air pressure to breathe. These birds evolve shorter wings or lose flight entirely. Land animals grow dense, powerful bodies. Trees grow wide, not tall. Humans, if still dominant, might look like compact tanks built for survival. Alternatively, we may retreat into domed cities, space stations, or orbiting rings, escaping gravity's grip. Scene 7. Space travel becomes nearly impossible. Escape velocity has doubled. Launching a rocket from this super-Earth would require more fuel, more energy, more risk. Satellites would fall faster. Space stations would need to orbit higher. Moon missions? Delayed indefinitely. Earth becomes a gravity prison, locking us down unless we develop nuclear propulsion, space elevators, or off-world launch bases. The stars feel further away than ever. Scene 8. The flow of time itself changes. According to Einstein, stronger gravity slows time. On this heavier Earth, time would tick fractionally slower than on the Moon or Mars. Atomic clocks would notice the difference. Deep inside the planet, time would move even slower than at the surface. It's negligible for daily life. But for interplanetary explorers, it adds up. Earth becomes a temporal island in the ocean of space-time. Scene 9. Climate chaos and plate tectonics. More mass equals more internal heat equals hyperactive geology. Earthquakes become stronger. Volcanoes erupt more frequently. Plate movements accelerate, mountain ranges crumble or rise faster. Combined with the greenhouse atmosphere, Earth might resemble a young Venus. Volatile, hot, shifting constantly. A world always changing, never resting. Scene 10. The future of life on a super-Earth. In the long run, humanity would adapt biologically, evolve new technologies, redefine architecture, reconsider its relationship with nature, or leave, abandon the planet. Seek lighter worlds. Become interstellar nomads, haunted by the place that shaped us. Earth wouldn't be unlivable, just unforgiving. Outro. Dramatic score rises as Earth spins under immense gravity, clouds churning violently. So what if Earth was 10 times more massive? Gravity would rule. Time would warp. Life would adapt. Or collapse. We'd learn that mass isn't just weight, it's destiny. Scene 1. What are cosmic gas clouds? These are interstellar clouds, and also called nebulae or molecular clouds. They range from cold hydrogen clouds stretching light years to dense stellar nurseries where stars are born, or supernova remnants filled with heavy elements and radiation. They're not empty, they're not quiet, and they're not harmless. Scene 2. How would Earth get there? The solar system orbits the Milky Way every 230 million years. During this galactic journey, it sometimes crosses dusty regions, hydrogen zones, or dense molecular clouds. Scientists believe this has happened before and may happen again. What changes depends on density of the cloud, duration of exposure, Earth's magnetosphere and shielding. But one thing is certain, the sky will never look the same. Scene 3. First signs, a strange new sky. At first, the stars fade. The gas cloud scatters light. The sky becomes hazy, milky, sometimes glowing. Daylight becomes diffuse, even tinted, pale green, violet, or golden. At night, auroras stretch across the equator. The moon glows dimly behind curtains of interstellar mist. Children grow up thinking clouds come from space. Scene 4. Atmospheric infiltration and chemical chaos. As we pass deeper in, particles from the gas cloud begin to enter Earth's upper atmosphere. Results may include chemical reactions with ozone, thinning protection, increase in cosmic dust, redder sunsets, darker skies, new elements raining down, possibly life-altering or mutagenic, rise in cloud condensation nuclei, chaotic weather, unusual storms. The planet enters a phase of atmospheric alchemy. We breathe air touched by stars. Scene 5. Global cooling or heating. Cosmic clouds can block sunlight, triggering cooling effects. Some scientists theorize that ice ages may have been triggered by past galactic cloud encounters. Alternatively, if the cloud is energetic or radioactive, it may heat the upper atmosphere, causing atmospheric expansion, disruption of satellite orbits, breakdown in climate systems. In short, predictability ends. Scene 6. The effect on technology and satellites. A dense gas cloud is filled with plasma electromagnetic radiation, dust particles. These interfere with GPS signals, satellite communications, power grids via geomagnetic induction, spacecraft electronics. The space age goes quiet. We return briefly to the age of wires and compasses, while trying to survive in a storm of space dust. Scene 7. Evolution accelerates or halts. Exposure to increased cosmic rays from the cloud could increase mutation rates, trigger genetic shifts in species, spark new evolutionary branches. Alternatively, radiation spikes could wipe out sensitive organisms, collapse fragile ecosystems, damage DNA on a planetary scale. We roll the biological dice. Earth becomes a laboratory of cosmic change. Scene 8. Philosophical awe. Earth in a living sky. Imagine standing on a mountain. The sky above you isn't blue or black, but swirling pink and teal, gas tendrils drifting like silk. No stars, no moon, just the living breath of the galaxy. People fall to their knees. Some worship, some flee, some record the light in silence. The cosmos has entered our world, and we realize we are not separate from the galaxy. We are inside it. Outro. soft music, and visuals of Earth wrapped in glowing gases orbiting slowly through the mist. So what if Earth passed through a cosmic gas cloud? The sky would melt, the weather would break, and life would be rewritten. But maybe, in the turbulence, we'd discover something more, a deeper connection, a galactic heartbeat, a living universe, and our fragile place within it. Scene 1. What is tidal locking? Tidal locking happens when a body's rotation period equals its orbital period. It always shows the same face to its parent, like the Moon does to Earth. Some exoplanets are tidally locked to their stars. If Earth became tidally locked to the Sun, one hemisphere would face perpetual daylight, the other would never see the Sun again. Earth would no longer spin, it would hang in space, half alive. Scene 2. How could Earth become tidally locked? Normally, Earth is too far and too massive for the Sun to tidally lock it anytime soon. It would take billions of years. But in this scenario, a cosmic collision slows Earth's rotation. A passing celestial body alters its angular momentum, or advanced alien intervention halts the spin. Whatever the cause, Earth stops spinning and the world divides. Scene 3. The eternal day side. A world of fire. The sun-facing hemisphere experiences unending solar radiation, temperatures soaring past 120 degrees, oceans evaporating into massive clouds, atmosphere rising in turbulent updrafts, a permanent hurricane system in the subsolar point. The land becomes desert, soil cracks, plants shrivel, human skin burns in minutes. It's a world too bright, too hot, too relentless, a place where fire rules. Scene 4. The eternal night side, a world of ice. The dark side, on the other hand, drops to 100 degrees and beyond. Atmosphere begins to freeze and collapse, oceans turn to glaciers, sky loses its color, becomes pitch black. Cities turn to tombs, but in this cold, stars shine bright. A frozen silence dominates. Time stands still in the dark. A world where ice reigns. Scene 5. The Twilight Zone, Earth's last habitable ring. Between fire and ice lies a narrow band, the Terminator line. Here, temperatures are tolerable. Water flows in rivers from melting glaciers. Wind constantly howls from pressure imbalance. A thin atmosphere fights to stay stable. This is Earth's last refuge. Civilization shrinks into a ribbon of twilight, clinging to balance between day and night. A world where you can walk from eternal morning to endless dusk in a single step. Scene 6. What happens to weather and oceans? With no rotation, the Coriolis effect disappears. Jet streams collapse, winds flow directly from day to night. The result? Constant hurricane-force winds toward the dark side. Gigantic cloud walls forming on the day edge. Water circulates violently. Ocean currents break down. Weather becomes brutal and one-directional. The planet breathes in long, chaotic gusts. Scene 7. Could life adapt? Yes, but it would change forever. Plants evolve to live in constant sun or perpetual dark. Animals become heat-resistant desert dwellers or ice-hardened nocturnals. Humans live underground or in sealed climate bubbles. Cities migrate toward the twilight zone. Energy relies on geothermal, wind, and solar harvesting from extremes. It becomes a planet of survival, of engineering, of strict geographic division. A world sliced in half, yet still 11 part is Scene 8. Philosophical reflections. One face, one fate. In this world, time isn't marked by sunrise or sunset. There are no days, only direction, toward the sun or away from it. People define their lives by light or shadow. The concept of time, language, culture all shifts. Perhaps one day, a child might look up at the horizon, where the sun forever kisses the clouds, and ask, what is night? Outro, slow piano, with visuals of Earth's Terminator band glowing faintly between extremes. So what if Earth became tidally locked to the sun? It would split into two worlds, one of relentless fire, one of eternal frost, with a fragile strip of hope in between. Scene 1. What are rogue planets? Rogue planets, also called interstellar nomads, are planets that have no star. Wander freely through the galaxy, range from Earth-sized to Jupiter-sized, or larger. Some may have been ejected from their systems. Others might have formed in the void. They are dark, hard to detect, and potentially deadly. Scene 2. How could one hit Earth? In our scenario, a Jupiter-mass rogue planet drifts through the outer solar system. It slingshots past Neptune, disturbing orbits. Earth's gravity locks into an intersection path. The rogue planet is massive, cold, and coming fast, tens of kilometers per second. No explosions, no warning, just inevitable collision. Scene 3. The signs before impact. Before the collision, strange phenomena unfold. Gravitational disturbances shake the orbits of outer planets. Tides on Earth grow erratic. The moon's path shifts. Aurorae blaze in unusual latitudes. Satellites begin to drift. And then it appears in the sky. A growing dark sphere, not emitting light, but blocking stars. Humanity holds its breath. Scene 4. The moment of impact. Global annihilation. The collision is not survivable. If the rogue planet is Earth-sized or larger, kinetic energy equals trillions of nuclear bombs. The crust is liquefied. The atmosphere ignites. Oceans vaporize. Shockwaves wrap the entire planet in minutes. The two planetary cores merge. Mountains collapse. Civilization ends. Earth doesn't just die. It becomes part of something new. Scene 4. Could we escape? Could we fight back? If detected early, as centuries in advance, humanity might attempt planetary deflection using gravity assists or nuclear propulsion. Build deep space arcs to flee the system. Construct underground survival vaults. But against a planet-sized body moving at orbital speed, the odds are low, the stakes are infinite. Earth becomes a target too large to move, too fragile to defend. Scene 6. Aftermath. A new Earth? A new world? After the impact, the two cores mix. A larger planet may form. A new moon may rise from the debris. In time, a new world could stabilize. It might have a molten surface. No atmosphere, but eventually, life again? Earth as we knew it is gone, but Earth's elements survive, scattered in the birth of a new world. Scene 7. Has this happened before? Yes, Earth's own moon is believed to have formed from a planetary collision with a body called Theia. That impact reshaped Earth, so while this seems like an end, it might also be a beginning. One violent act, one dead world, one rebirth. Scene 8. Philosophical reflection. We are not alone in the dark. The galaxy is full of silence, but not emptiness. Rogue planets, black holes, neutron stars, drift without purpose, without pattern. Earth floats in a narrow window of peace. But one knock, one shift, and everything we know ends. This is the nature of the universe. Beautiful, violent, indifferent. Outro. Emotional music swells as Earth and the rogue planet collide in slow motion, fading into a new glowing sphere forming in space. So what if Earth was hit by a rogue planet? It would be the end of everything we remember, but maybe the beginning of something greater. Scene 1. What are rogue planets? Rogue planets, also called interstellar nomads, are planets that have no star. Wander freely through the galaxy, range from Earth-sized to Jupiter-sized, or larger. Some may have been ejected from their systems. Others might have formed in the void. They are dark, hard to detect, and potentially deadly. Scene 2. How could one hit Earth? In our scenario, a Jupiter-mass rogue planet drifts through the outer solar system. It slingshots past Neptune, disturbing orbits. Earth's gravity locks into an intersection path. The rogue planet is massive, cold, and coming fast, tens of kilometers per second. No explosions, no warning, just inevitable collision. Scene 3. The signs before impact. Before the collision, strange phenomena unfold. Gravitational disturbances shake the orbits of outer planets. Tides on Earth grow erratic. The moon's path shifts. Aurorae blaze in unusual latitudes. Satellites begin to drift. And then it appears in the sky. A growing dark sphere, not emitting light, but blocking stars. Humanity holds its breath. Scene 4. The moment of impact. Global annihilation. The collision is not survivable. If the rogue planet is Earth-sized or larger, kinetic energy equals trillions of nuclear bombs. The crust is liquefied. The atmosphere ignites. Oceans vaporize, shockwaves wrap the entire planet in minutes. The two planetary cores merge. Mountains collapse. Civilization ends. Earth doesn't just die. It becomes part of something new. Scene 4. Could we escape? Could we fight back? If detected early, as centuries in advance, humanity might attempt planetary deflection using gravity assists or nuclear propulsion. Build deep space arcs to flee the system. Construct underground survival vaults. But against a planet-sized body moving at orbital speed, the odds are low, the stakes are infinite. Earth becomes a target too large to move, too fragile to defend. Scene 6. Aftermath. A new Earth? A new world? After the impact, the two cores mix. A larger planet may form. A new moon may rise from the debris. In time, a new world could stabilize. It might have a molten surface. No atmosphere. But eventually, life again? Earth as we knew it is gone, but Earth's elements survive, scattered in the birth of a new world. Scene 7. Has this happened before? Yes, Earth's own moon is believed to have formed from a planetary collision with a body called Theia. That impact reshaped Earth, so while this seems like an end, it might also be a beginning. One violent act, one dead world, one rebirth. Scene 8. Philosophical reflection. We are not alone in the dark. The galaxy is full of silence, but not emptiness. Rogue planets, black holes, neutron stars, drift without purpose, without pattern. Earth floats in a narrow window of peace. But one knock, one shift, and everything we know ends. This is the nature of the universe. Beautiful, violent, indifferent. Outro. Emotional music swells as Earth and the rogue planet collide in slow motion, fading into a new glowing sphere forming in space. So what if Earth was hit by a rogue planet? It would be the end of everything we remember, but maybe the beginning of something greater. Scene 1. What could make Earth's orbit shrink? Normally, Earth's orbit is stable, held in perfect balance by gravitational forces. But it's not immune. What could cause it to spiral inward? Drag from the solar wind. Massive gravitational interactions with other bodies. A sudden loss in Earth's orbital velocity. An advanced alien civilization altering our trajectory. Or even human error from megastructures or large-scale space engineering. Whatever the cause, our orbit begins to decay. Scene 2. At first, nothing seems wrong. In the beginning, the shift is almost undetectable. Earth draws just a few kilometers closer each year. But small changes matter. Solar radiation increases. Temperatures rise subtly. Glaciers retreat faster than expected. Seasons stretch and warp climatologists blame global warming. But something deeper is at play. The sun isn't just brighter, it's closer. Scene 3 decades later. The slow burn begins. Within 100 or 200 years, average global temperature rises by 10 to 20 degrees. Ice caps vanish completely. Sea levels rise catastrophically. Deserts expand into former forests. Coral reefs bleach and vanish. Humanity enters a global migration phase, moving inland, upward, underground. Cities are buried. Coasts disappear, but there's no escape from the heat. Scene 4. Atmospheric breakdown and chemical change. As Earth gets closer, the atmosphere thickens, then destabilizes. Ozone layers break down under intense UV methane and CO2 levels. Spiral. Rain becomes acid-laced. Jet streams collapse eventually. Runaway greenhouse effect sets in. Like Venus, skies turn gold and orange. Clouds become reflective traps. Storms become permanent, global, and electric. Scene 5. Water reaches its boiling point. Around 140 million kilometers from the sun, just 10 million kilometers closer than we are now, oceans begin to boil. Not boil away instantly, but slowly vaporize. Humidity rises to unbearable levels. Rain falls superheated. Rivers dry from both ends. Steam fills the lower atmosphere. Eventually, Earth's surface becomes a pressure cooker. What remains of humanity goes deep, into bunkers, geothermal shelters, or orbital stations. Scene 6. The death of the biosphere. Plants die first, then animals. Photosynthesis becomes impossible. Pollinators vanish. Food chains collapse. Insects mutate or go extinct. Birds fall from the skies. Fish boil in shallow seas. What's left is microbial. Extremophiles clinging to vents, shadows, cracks. Life doesn't end instantly, but it's dying in slow motion. Scene 7. Humanity's final age. If we survive, it's because we adapt or escape. We build orbital habitats with artificial gravity and solar shielding. We colonize the Moon, Mars, or asteroids. We launch interstellar arcs to Proxima Centauri. We build a planetary engine, a stellar tug, pushing Earth outward, a solar sail, a gravitational slingshot, a magnetic planetary drive. But all come with a cost. Earth's identity fractures. We are no longer bound to home. We are migrants of necessity. Scene 8. Final approach. Earth at the edge of survival. Eventually, Earth enters the inner orbit of Mercury. The sun fills half the sky. Temperatures exceed 500 degrees, surface rock melts. The crust becomes soft. The magnetosphere collapses. Solar flares strike the planet directly. It's no longer a world. It's a memory, spiraling into fusion. Scene 9. Philosophical reflection. The slow death of Eden. Unlike an asteroid or a sudden black hole, this is a death by proximity. A slow, graceful fall into oblivion. Each year warmer. Each season shorter. Each generation more distant from Earth's original beauty. And still, the sun calls us closer. The flame that once gave us life now takes it back. Not with malice, but with inevitability. Outro. Soft piano fades as Earth, glowing red-hot, vanishes into the blazing corona of the sun. So what if Earth's orbit was shrinking into the sun? We wouldn't see the end overnight, but we'd feel it, year by year, decade by decade, until only light remained. Scene 1. The concept of a binary star system. Binary star systems are common in the galaxy. More than half of all stars have a stellar companion. They come in close binaries, where stars orbit tightly. Wide binaries, far apart but gravitationally bound, eclipsing binaries, creating rhythmic patterns of light. If Earth existed in such a system, everything would be different, from orbits to seasons to survival itself. Scene 2. How Earth could gain a second sun. This could happen in a few wild scenarios. The Sun captures a rogue star into a stable orbit. Earth is ejected from the solar system and captured by a binary system. A massive stellar engineering project creates an artificial second sun. Or we terraform a brown dwarf into an ignition point nearby. Whatever the mechanism, the result is the same. Two burning giants in our sky. Scene 3. Gravity unbalanced. Orbital chaos. With two suns, Earth's orbit becomes highly unstable. Seasons become erratic. Years stretch or compress unpredictably. Nights become rare, fleeting, or non-existent, depending on the configuration. We may orbit one star, with the second far off. Or both stars may orbit a common center, dragging us in looping paths. Either way, predictability ends. Scene 4. Daylight doubled, a world too bright. Two suns mean longer days, shorter nights, higher UV radiation. More solar storms. Temperatures rise dramatically. Deserts spread. Ice caps melt completely. Equators become uninhabitable. Cloud cover thickens, then collapses. Even photosynthesis begins to fail, overwhelmed by intensity. Sunburn becomes fatal in minutes. The world is not just warmer. It's scorching. Scene 5. Twin shadows, twin tides. Two suns cast, dual shadows, shifting and overlapping. Twilight that glows from opposite directions, constant illumination in polar regions. And if the second sun has its own planetary system, gravitational interactions could stretch Earth's tides, disrupt the moon's orbit, trigger massive tectonic instability. The Earth groans under the weight of two giants. Scene 6. Atmospheric disruption and magnetic danger. More sunlight means increased ionization in the upper atmosphere, collapse of the ozone layer. Frequent geomagnetic storms. Auroras become global, but so do power grid failures, communication blackouts, satellite destruction. The space age falters under solar assault. Scene 7. Could life survive? Could we adapt? Possibly, but at great cost. Architecture evolves with radiation shielding. Cities migrate to eternal twilight zones. Humanity lives underground or beneath reflective domes. Agriculture uses spectrum filters and artificial environments. Plants are re-engineered to withstand double light. Animals evolve or perish. Humans become creatures of the shadow, hiding from the sky. Scene 8. Cultural shift. Two suns, two myths. In this world, calendars must account for dual orbits. Religions may divide between the first light and second flame. Languages develop words for overlapping shadows. Time itself becomes fluid, shaped by two stars. Children grow up watching two sunrises, thinking it's normal, but the world they inherit is constantly shifting. Scene 9. A poetic universe, beauty and burden. Two suns in the sky. It sounds like a painting, a dream. But with beauty comes burden. The Earth is overfed with energy. Its systems crack. Its life adapts or dies. We marvel at twin sunsets, but we also mourn the price of light. Outro. Majestic strings as Earth rotates under two radiant suns, the planet glowing at every edge. So what if Earth had a second sun? It would be a world of brilliance and peril. A land of two dawns and too much day.